Okay. First of all, special thanks to the organizer, because giving a talk here on this subject for me is a special meaning. I met Cyrano, I think, end of 90s, but I started work with him in 2003, something like this. And our collaboration was continuous. I came several times here since then, working on our common project of spin glasses, and lasted till the end, till when the malady was taking him from working. I also visited him several times when he was in the hospital. And so for me, staying here and speaking about work with Cyrano is something particular. And for the same reason, what I think is the best way to remember him is to present something we did together. And in this almost 8 years we worked together. We did several things, and the idea was always to try to somehow merge the spin glass, in the spin glass, the replica solution with the droplet theory. This was our main stream of research, and we did several attempts. And the one I've chosen to present is the last one we did. It was also the last work of Cyrano. This is also why I've chosen these things. And so I apologize for people that already listen to these seminars, but I think this is some special, because in some sense it gives a full view of the work of Cyrano, because Cyrano, as was already said, was really doing calculation and was really nice in doing this. And you will see in this talk somehow his style of working and what he did it. I will try to keep these things as simple as possible, because doing calculation is not so nice on this, and then we have just to sit and this. But I will try to give you the feeling. Okay, so why we study these things? Okay, as already Mike yesterday said, one way of studying the approaching stability and decide if the solution is good or not is just to study fluctuation about a solution. And so in this case, the fluctuations are computed in the replica theory. And Cyrano with Imri and Tamash calculated the spectrum of the fluctuation. This is one paper, which is, if you read it at the first time, it's quite hard to understand, but you have to really to see it and bear using pictures and so on. But even if you compute this, then you have to take this, put inside the second order fluctuation, and try to build loop corrections, which is not so easy. And so we had to, if one can try to find some region where these fluctuations, this can be computed more easily, this will be very important to try to understand if the stability of the solution. And moreover, at t equals 0, in some sense, it's really the domain of droplets, because droplets is built from excitation from t equals 0. So pushing the study not close to the critical point, but exactly on the other side at t equals 0, may give some hints of this. And it turns out that the two things, in some sense, achieved simpler solution and inside the real region of droplets. Unfortunately, the work is not, this is just the starting, because then we finish, but okay. So in some sense, this is the outline, so we try to keep this simple and explain you how we computed this and why we did some kind of calculation. So that was Anderson model. everybody almost know. It's a very simple model. In some sense, we have some Ising spin, which takes value plus minus 1, which sit on a lattice, the d-dimensional lattice, for example, cubic lattice. And they are coupled by some random interactions. Say they are taken from Gaussian distribution with zero average. We do not want some extra order, and the variance scales with some rules in order to have a good, well-defined thermodynamic limit, something which is related to the number of neighbors or coordination numbers and so on. It looks like a sort of simple and trivial model, but it's not so. The problem comes from this, as already just in the talk of Francesco. The problem comes from the average, because if we want to do the thermodynamics, we have to compute the free energy for fixed configuration of the disorder and then take the average. And the average of the lock is not an easy task. So one way of doing this is using replica, this replica trick, and which just means taking n identical replicas and average this, and then one take this n to 0 limit in some way. But the main point is that when we do this, we gain, because in some sense our problem diagonalizes in the space, but we get interactions in the replica space. So the replicas that at the beginning were independent now start to interact with each other. And one can write down this in terms of a field theory with this, where QAB is an order parameters, which has two indexes, which are replica indexes, but the number, since due to the symmetry, the numbers of free field components is just n times n minus 1 over 2. Okay, this okay, so the idea then is to develop find a solution which is simpler, and the solution is something which does not depend on the site, which is a mean field solution, and expand around this solution. So this means one introduce this Q and expand, assuming that the delta Q AB is small, one just expand the action L in terms, and the first terms turns out to be the mean field solutions, or the Sherrington-Kirkpatrick functional. The next term is what fixes the value of QAB, because QAB at this point is freeze, is still not fixed, and this is taken by imposing that the first variation is 0. This, in terms of field theory, means that the theory contains no tadpoles. So we are just summing up all tadpoles, and we get these solutions. The next term is the one which is interesting to us. It gives the Baire propagators of the theory. Now you can see that it contains two terms. One term which is just trivial, which is p squared, which is the kinetic terms. But then we have another term which is just the mass term, which is the Hessian of the stability Hessian of the Sherrington-Kirkpatrick model. And all these averages must be evaluated, assuming the known form of QAB. Depends on how we choose this parameter QAB. Next terms, 3, 4, and so on, they just give the vertex of the theory, which has the basis to build up the corrections. But the problem is that everything now depends on this function QAB, and which must be solved self-consistently from this equation. In principle, we have no structures. There is no hint on the structures. And we know now that to solve this, one has to break the symmetry, the original symmetry among replicas. The physical meaning is that we have these landscapes that breaks down into different regions, and then we may have different replicas, if you want, sitting in different regions, so we have to account for this. Now, there are several ways of doing this, but the most transparent and the one which is winning over the others is the Parisi scheme, which is based on a hierarchical construction of the model. I will just go very fast, but because I need this to fix how the notation, how we will work. Okay, the first step is just a symmetric case, so it means every pair of replicas have the same couplings. So, okay, thank you. Okay. So it means that that all entries in the matrix are equal, and on the diagonal we should have 1, but I take Q0 for simply for the notation and to have a better generalization of this. Okay. Yeah. Tricky. Anyway. Okay, now we go to the next step. So it means now it's the same. We have replicas. We just divide it into two groups. One, and if the replicas are in one group, they have one overlaps, and if they belong to different groups, they have different value. This just means that we divide our metric into blocks. Okay, and we have different value, Q0 if they are on a different groups, and Q1 if they are on the same. Okay. Now, to represent this, it's useful not to use only one index A, but split A into two values, A0 and A1. One which gives me the position in the largest block, and the second one which gives the position in the second block. This is why, because if now I proceed and do another step, which means that I take replica inside one region with Q1 and divide it into other region and so on, I can just do this very easily, and representing this, we're introducing three now replica indexes, which one gives me the largest block, then the second block, and so on. So now you understand that we can easily extend this to any number of replicas, and saying that replica A and B, they have an overlap QR, which we can identify with A and B equal R, if they have the indexes from 0 to R minus 1 equal, but the R indexes are different. In this way, this has a very simple graphical interpretation. We can just draw a binary tree and represent on the bottom the replicas, on the top is the level 0, and then they just split at the level R. Okay, this is quite trivial for this, but it turns out to be quite useful, because now, remember, if we want to study the mass term, we have to deal with the things that have 4 replica indexes. So we have to find a way to represent possible configuration of these things. Now, it turns out that for these systems, where we have 4 replicas, where we have 2 possible topological representations, which are completely different. The so-called replicon sector, or replicon configuration, and the longitudinal anomalous configuration. How do we represent this? Okay, the replicon geometry is this one. It occurs only if the overlap, the cross overlap between replica A and B and C and D is the same. And the other one are denoted by U or V, and for this configuration, we need the 4 replica indexes to specify completely the configuration, which are 2, the cross overlap between A and B and between C and D, which are the same, but actually there are 2. And then we need other 2 rep indexes, which are E and V, U and V, which just gives me the others. The longitudinal anomalous geometry is this one. It occurs if the overlap between A and B and C and D are equal or different. It doesn't matter. And a difference with the others, now 3 cross overlaps are sufficient to completely specify the configuration, which are 2, the cross overlap between A and B and C and D, and 1 which gives just the maximum of the cross overlap between A and C and D and B and C and D. Okay, so once we know this is the configuration we have to deal with, and if we want to compute the masses, we have to solve this problem. This is just to find the eigenvectors and eigenvalues. This was solved in some sense by brute force by Imri, Cyrano, and Tamash, just looking how the matrix looks like for the replicon or the longitudinal anomalous configuration and build up the eigenvalues and associated eigenvectors. But a little bit later, also Cyrano realized, and developing a sort of transform, that these things can be done in some sense, I won't say more elegant, but easy, but one can in a different approach using, starting from this. You know, if we have this equation, we know that we can just diagonalize in taking the Fourier transform. So the idea was to do the same, but on the replica space. Now, this is a little bit more difficult because we have these structures in the replica, so one has to generalize this concept of Fourier transform to this geometry. And this is done what is called the replica Fourier transform, for which Cyrano was really a master on this. I won't go into the detail of this. I just give you the basic idea to understand. This is defined this way. If we have a function which is function of the replica index, then we define its Fourier transform on the replica space just by summing over all possible value of A with this kernel. And this kernel, in some sense, is just a sort of Russian doll in which we have Fourier transform of each scales, in some sense. Now, you can easily verify that this satisfies this equation, this identity, so we can just invert the Fourier transform. And from this, you derive some useful result. For example, if we have a function that depends only on 2 indexes, which are A and B, and we have this, and the overlap is R, then we can easily compute the Fourier transform, which is AK, and going back. So we can just relate one to the others. And for example, you can also prove that if you have a matrix product, then the Fourier transform of C is just a product of the Fourier transform of the other 2, from which you can easily compute the inverse of the matrix without doing any complicated calculation. But you can also see that in this case, the Fourier transform just diagonalize the matrix, and the AK are the eigenvalues in these things. Okay, let's see how we do this for this problem. Okay, the idea is quite easy. We take the Fourier transform of this with respect to 4 indexes, and then we end up with this equation that must be solved. And you also write down the Fourier transform of the matrix, separating the longitudinal and the anomalous. I won't go into the details of the calculation and give just the result, because it's boring. And so it turns out that if we just look at the replicon sectors, this procedure just diagonalizes the matrix. So we just get the eigenvalues, and these are the eigenvalues which are just a double Fourier transform. In the longitudinal anomalous sector, is not so, we are not so likely, because it does not diagonalize the matrix, but it's just reduced in blocks. So I mean a sort of journal reduction. So we cannot just have directly the full eigenvalues. We have still to solve a problem, and we have still to diagonalize blocks matrices, but of smaller dimension. In any case, we can just write the equations. Okay. Now, this was derived also by Imri and Tamash and Cyrano from direct calculation in the replica space without using the Fourier transform. So, but if we want to proceed, it's not enough to write down what are the expression of the eigenvalues. We also have to compute the eigenvalues and see what are the real value of this. This means that we have to compute these coefficients, which are MRST or MRR, UV, and so on. And this, it turns out we have to compute the averages of 4 spins. So the problem is how we do compute these things. Do we have, if I want, even numerically, how do I do this? Okay, the idea is quite simple. We go back to text, and how we do, if you want to compute the average of something, we can just introduce a generating function, which is in this case is this quantity, and then the averages can be just computed by taking the derivative with respect to the auxiliary field we put, which is B, and then setting it to 0 if we do not want an external field, or setting whatever we want if we want to have an external field. Okay, so far so good. This is general, but the interesting point is that due to these structures of the replica space in sort of shells, we can integrate this shell by shells in some sense. What is the problem in this? The problem is that we have a bilinear term, which is SASB. We know how to transform this into a linear term, which is just by Satanovich-Alba or Gaussian transformation. We cannot do this directly here because we have these structures, but we can do separately on each levels. So this just means that we introduce a set of auxiliary field, this Z, which allow us to integrate down to the lowest level, where we have only one spins. And so we start from the beginning, which is just this quantity here, which is just one spin in a field. Okay, we have done this in one direction, but now we can go back. And we can calculate things just integrating out step by step. Just to have an idea, just consider Z node, the normalization. So if I take this BR, which is this auxiliary field, and split out the contribution from the level R, I can integrate out this, keeping all other fixed. And if I just define a new function G by this recursive relation, you see that I get formally the same expression I had at the level R. So I can proceed. So I can now split out the second R minus 2, integrate it out, and continuously integrate this until I reach the higher level. In some sense, I'm just climbing up the tree, up to the top. And so I get an expression for this function, which is G naught. This is actually is the free energy of the model. These things is a trick, appears as a mathematical trick, but actually it has a physical meaning, which is the following. Consider this. What is this GR? This is just the free energy of a single spin in a field. So it's the lowest level. The smallest group we can do is just one spin. Okay, and so we can interpret this as the free energy density of a system of one spin in an external field, which is a random field. Now we want to move one step up. So what do? We integrate out this ZR. Okay, this means that we integrate everything, all Z, at level R, but keeping all other with the index T smaller than R fixed. What does this mean? This means, in some sense, that ZR is the actions. I mean, in some sense, give the information on the other spins which are outside this, which are on the higher level, so are outside these blocks, are on the other blocks. These are kept frozen. Okay, so this means that we are integrating all the spins that have a sort of, which are very close, keeping all other fixed. In other words, we sum over all spins that have an overlap, cross overlap R, but all other are fixed. So we are just making together spins. And so we are just doing a sort of thermodynamics inside with this, the lowest group we can do. So we can interpret this G as a free energy density of a system of size PR. Okay. But there is an external field which gives me the information on the state of other spins, which are frozen at this level. I cannot move. So this means that when we keep integrating and climbing the tree, what we are doing, we are just taking blocks of spin, putting together, taking all others which are on the other blocks frozen. Okay, so we are just if we want to see this as height of free energy barriers, we are just integrating, starting from the lowest free energy barriers and then climbing up. Or better, in a sort of dynamical picture, because after all, physics, the word is dynamics, it means that when climb up the tree, going up, it means that we are free and frozen. We keep frozen some degree of freedom, but at the same time, we unfreeze some others. So in some sense, we are integrating out over the degree of freedom that have smaller characteristic time, keeping the others. So in some sense, we are just moving along the time, just freezing and unfreezing different degree of freedoms. Okay. I will come back on this just at the end. Okay. Now, this give a hint how we can compute this spins averages, because suppose we have a function which is a generic function which is just function of the local fields we have at some scales. Now we want to move to the next scales. How we do this? We have just, since moving from one scale to the next one, it just means that we put together spins and we average of this. On the next level, this will be given just by the average of these functions on this, of the spin of this level, weighted with the correct Boltzmann weight. So this means that we have this kind of recursion relation. Okay. Okay, let me just give you an example so to see that this makes sense. Suppose we take as this function just the derivative of this. This is the magnetization at the central level. It's easy to see that if we use this recursion relation, we just get that at the next level, it's just given by the derivative of g of the next level. And so we get the usual form for magnetization, which is in this model, which is just given by this expression. Okay. Now let's do something a little bit more difficult, which is the 2-point averages, which is just the order parameter. Now, what I have to compute is this, because at the lower level, I just replace the derivative by m, and this is what we have at the lower level. Now we want to climb up and start integrating. Now we see that up to level r, scale r, there is no problem, because the two just belong to different branches, so we can just integrate it independently, one and the others. The problems arrived at r. So let's do the first integration from capital R to small r, and when I reach this point, I get just that the two m are the same, because I'm just climbed up two different branches, but the result is exactly the same. So now how can I move from this to the top? But it's very easy, because now what I do, I just introduce a function which is just this that I call m2, just to remember that it's just given by the merging of two m, which has a boundary condition which is just at the level r is just the product of the two m. And then I just use the recursive relation I give you before, and then I can just write an explicit form of this quantity. Now let's go to the fourth. It's clear that now to compute this we have to specify the geometry, otherwise we cannot just climb up the tree. But so let's take a generic longitudinal anomalous configuration, and so it's quite easy now, because you see now we can climb, the replicas are independent up to scale t. So if I integrate from capital R to t, when I end up at t, the branches A and D, they are independent, so they just keep to be m. The other two merge, so I get a square, exactly as before. Now, starting from this, I can climb the tree up to scale R, and this is done exactly as I did before with this function m2, which has this boundary condition. And then at this point, the branches A, B, C, D just merge, so I need another function to climb to S, which is this, what I call 2, 1, which means I start from 2 and then get 1. Another branches, and so on. So I can, in this way, I can write down the equation for any kind of spins, averages, for whatever you want. Okay, but now we know that to solve the problem, we have to take the number of replicas to infinity. And in this limit, the matrix QAB becomes a continuous function, smooth function, and where x is a parameter. It can be anything. But what is one of the useful choice is to introduce this x of q, which is just the probability of observing a value in overlap q, smaller or equal q. So we have now just to take this continuous limit on the recursive relation we have before. So in this limits, what we have R becomes continuous, and lambda, so the eigenvalue lambda R becomes a function, the equivalent of Q of X. And then in the function, this function I've introduced becomes function of X, which is the level, and B, the local field. So we have just to take this equation and see what happens in this limit. Now, this limit, when I move from one level to the other, it means I do an infinitesimal changes on the parameters because S and R becomes continuous. So plus 1 or minus 1 is just an infinitesimal change. So with a little bit of work, one can translate this into this differential equation, which are the basis if you want to compute these things numerically. Okay, and where, as usual, I denote by a dot the derivative with respect to the scale, x, and the prime, the derivative with respect to the external field. Okay. Now that we have a setup, we have just to see what happens when t goes to 0. Now, when t goes to 0, the function of u of x has this behavior. Okay, the breaking point above which it's equal 1 stay finite. It's a value about 1/2. But q of 0 is 0. So what we have is that this q of x flatten close far from the origin. And in the limit, t going to 0, because it develops a boundary layer with t around t equals 0. So for t equals 0, the overwhelming part of the q is given by what is called the outer region. So if you want to study what happens for t going to 0, we have to see what happens in the outer region. If you want to construct corrections, we have also to include what occurs in the inner region. But for the moment, I will just consider the outer region. So we have just to study what happens outside. And to see what happens outside, I have to compute the solution of this differential equation I've introduced in the outer region. This can be done using a scaling introduced by Pankov, which means that we take this equation and we introduce an auxiliary variable, which is just given by the product of beta, x, and z. And if we write this in this form, we get this equation. Okay. Now, in the other region where it flattens, the dependence of the scales must disappear. So this means that this f becomes independent of x, this function f. And this is possible only if this quantity here become a constant. And from this we get the scaling of q of x outside, which was also computed in a different way. So this means that in the outer region, q of x takes this form, which means that the difference between q of x for x generic and x at a critical point is of order t squared. So if we do the calculation to the lowest order, we can just forget about this and keep constant. This means for our point of view that we can just consider q of r constant if the associated q of x of q, it's much larger than t, or if I fix the scale r when t goes to 0. Because if I fix one point and let t go into 0, I will enter in the outside region. No, for sure. So what are the consequences of this? Well, the consequence of this is the following, that in the outer region, so it means when the index r is such that p of r is much larger than t, this quantity do not depend on the lower indexes u and v. And if this is so, then the eigenvalues of the replicon sectors are of order 1 over S squared. This can be proved using the Bartolowski identity. So they all vanishes. So it means that the complete band in the replicon sector just shrinks to 0. It cannot be negative because this identity prevents from going to 0, but it all vanishes. What happens in the longitudinal anomalous sector? Okay, again, here we have that the Fourier components are independent of K and L, and so the eigenvalues equation reduce to this form. Now we have two possibilities. The first case where this sum is 0, which gives me that all the eigenvalues are 0. Or I get that this is different from 0, and then I get the eigenvalues stay finite. Since time is running out, let me just do some conclusions. So what we have found? Okay, we have found that in the limit t equals 0, the replica symmetry broken part of the order parameter q of x shrink to 0, and we have something which flatten. And consequence of this is that all eigenvalues just goes to 0, all in the replicon sector, a part of the longitudinal anomalous vanishes, and one part collapses to a finite value. So of the whole spectrum, we have only two values, which is much simpler than the full spectrum we have in the general case. What is interesting is that if we do the stability analysis of the replica symmetric solution, what turns out that we have a similar scenario, at least to the first correction in T. So in some sense, this goes in the direction of, in some sense, putting together the replica symmetry broken solution with the droplets, because droplets actually is a sort of replica symmetric solution. So it looks like at this point that going to 0, we get something which resembles in some sense this scenario. Clearly, one has to go beyond this and see if there is really a sort of coalitions of the two or whatever it is. But at least this is a good sign. We have got something which resembles. And just to mention a few side products that I've presented these equations, this differential equation or this recursive relation in this form. One can reformulate this in terms of local field, the distribution of local field, using, and so going to the direction of the formalism of Sommers and Dupont. This is quite useful because this can be, then one can write this equation on a computer and solve it using some numerical calculations. It can be done. So it gives a quantitative method to compute eigenvalues for any kind of, for any temperature. Another interesting thing is that these things can also apply not only for this model, but for example for p-spin models. In this case, one can show that for p-spin models, one has a weak theorem on the tree, on the replica tree. In other words, for p-spin models, you can just open products of any number of replicas as a weak sum, and then just replace the Q. So this also opens the way of trying to study perturbation about the spherical models. And this was one other way we tried to do in these things. The last things is that with this you can compute the susceptibility at given scales. And it turns out that the susceptibility is given by width PR, the difference of the Q. And this is exactly the same, the static limit of the susceptibility you find in the formulation of the dynamics we did together with the Sommers and Horner for the spherical model that you can generalize to also to any number of broken steps. So I will stop here. I just give you the references where these things have been published, where you can find all details of the calculation if you want, because, okay, thanks for your attention.
Could I ask a question about what could be the next step in this kind of program?
Okay, the next step we had.
Could I suggest?
Of course, I can tell you what we had in mind. But
my suggestion, or the point of view, trying to find a connection to the droplet model, would be to calculate the energy difference
yes,
between periodic and antiperiodic.
this was one of the things we thought to do. Because once you have this, in principle, this is one thing, and the second thing that we had in mind, it was to try to compute the correction, the first correction to the eigenvalues in T, starting from this, and see what happens, how this modify this. But you have to take into account that this small part, which has a full replica symmetry state. This, in some sense, can be in the method of Hopper and these things, scaling on Hopper that to go inside and try to match the two things. This was another things that we planned to do. I mean, I've told you, this is just the starting point. Probably is the most promising result we had. Alas, it was the last one of Cyrano, but
for any temperature, if you're working above the threshold x1, this
yes,
breaking point, then you are calculating things referring to one single value. Right? So, for example, correlation functions inside a single value. And now that you go down to low temperature, this thing is taking over. Right? Apart from this small initial part, you are basically sitting in one valley. So this is the secret of this correspondence.
Yes.
Droplet thing.
Yeah, but if you do in this way, I mean, this, why we did this way, because we have a systematic way if you want to introduce corrections. So you have a way of computing this thing, this differential equation. It was also used by Pankov to study the crossover inside and outside. And you have a systematic way in principle to introduce corrections to this. Otherwise, it's just, what you say is correct, but the idea was just also to have something which you can then use if you want to improve your calculations.
Okay, well, if there are no more questions, let's thank Andrea.